everyone, let's go over this. You've had a second to look at this. The question was, which values of x make this a true statement? Any volunteers on what you did here, your thought process, or you're going to make me call on someone? What are you thinking, Alex? She's wanting to share something.
So for x cubed and then x squared, I just factored that and I took out x, and then I did factoring, and I got x minus 3 and then x plus 1, and then below that I did x plus 2 and then factored the other one, which I got x minus 3 and then x plus 1, and then I crossed out the ones that were.
Whoa. Sorry, my pen kind of went all weird on me. You said, what was this one, x?
X plus 1. And then I crossed out the ones that were the same.
Alright, so which ones were the same?
Well, x minus 3.
Oh, wait, in the top, I think I forgot something.
Yeah.
You said it was x minus 3 and then x plus 2, right?
Yeah.
And then x plus 1. I was trying to keep up with you and I missed that one. Okay, so then when I cross it out, goes away, goes away, goes away. So then, what does it become? Now, so here, yes, you are right. But let's make sure everyone's here with Allie. So Allie did a great job of simplifying this, and we were able to cross things out, right? Are you with her so far? Do you have any questions? Now, the original question was, what values of x could I plug in to make this a true statement? And what did you say, Allie? Keep going with it.
Negative 3 and 1. Or it would just be negative 3 and 2. I don't know. I was like, I don't know. So I was like, maybe it's the opposite.
Okay, so now we'll pause. Let's just focus on this statement here for a second. We'll come back to what you're saying. What values of x could I plug in there to make it a true statement? If I plug in 3, is 3 equal to 3? If I plug in 8, is 8 equal to 8? If I plug in 1,000,000, is 1,000,000 equal to 1,000,000? So the answer is, I could plug in any value, except what? Go ahead, Hiram.
Negative 2, 3, and negative 1.
Why could we not plug in negative 2, 3, or 1, Hiram?
Well, negative 1.
Or negative 1?
Because it makes it so you divide by 0.
And what happens when you divide by 0?
You blow up.
Right? Bad things happen. Yes, okay, so great. When we were talking about rational equations, way back in first quarter, I think it was, we talked about your excluded values and how even if you cross them out, they're still excluded, and we don't use those excluded values. In this case, what do those come? Do you remember if we graph this, what do those become when you cross them out like that? They're holes in the graph. Good job, so they're not part of our domain. So here, our answer is going to be all real numbers. Make this a true statement, except x cannot equal negative 2, 3, and negative 1. Now, what this is right here, this is an example of what is called an identity. It is a statement that simplifies to a true statement like x equals x, in which the solution can be everything, except whatever makes it divide by 0. We don't want to divide by 0. This is the kind of thing that we're going to do today, except we're going to apply it to trig. We're going to talk about trig identities. Have you ever heard of that word before, trig identities? Maybe like if you have an older sibling and they're complaining, they're saying how much fun they are. Yes, that's what we're going to do, okay? All right, so objectives today. First off, we're going to talk about basic identities, reciprocal identities. Then we'll get to Pythagorean identities, and then do some simplifying. We also want to make sure we watch out for our domain of validity. Okay, so let's just dive right in real quick. What is the difference between these two right here with the equation versus an identity, okay? So I'm going to pause and give you another 2 minutes here. I want you to find the solutions to these two statements, okay? So this should be something that you've done before. It shouldn't take too long. Let me give you 2 minutes on. Try to work through this and find the solutions to the two different equations. give you about 10 seconds till we start talking about this. All right, Mike, I'm going to ask for your help on this first equation. How did you find the solutions here?
You start with the equal to 0.
Uh-huh.
Subtracted 5x. And added 6.
Great.
And then I just thought, what two numbers multiply to 6? And then added to negative 5.
Awesome. What were those numbers?
Negative 3, negative 2.
Great. Keep going.
And then set equal to x. Add 3 and add 2. X is 3.
Do you guys agree with that? And I can check it by plugging it in, and sure enough, it gives me a true statement. 9 is equal to 15 minus 6, which is 9. 4 is equal to 10 minus 6, which is 4. Great job. All right, who wants to take the second one? It's not too bad. I'm going to call Mikkel. How would I simplify this one?
So, when dividing the numbers, basically just subtract them. So, 5 minus 3 is x squared. So, x squared equals x squared, which is x equals x. So, the answer is all real numbers, but x can't be.
Why can't x be 0, though?
Because 0 cubed is 0 multiplied.
What do you guys think? Spot on. Nice job, both of you guys. Okay, so perfect. This is an example of an equation. It has solutions, but the solutions, it was like maybe one solution or two, or maybe it has multiple. But how many solutions does this have? Infinite, right? You could plug in any number into that, and it would give you a true statement, except what number can you not plug in? 0. All right, cool. So now we're going to talk about domain of validity for some of our trig statements. Now, we're going to start off talking about some basic identities here. For example, we have our reciprocal identities. So when we started this year off, we refreshed ourselves with SOHCAHTOA, and we were all very familiar with SOHCAHTOA. And then we said, let's do the reciprocal trig functions. And I don't think you were as familiar with those, right? What are the reciprocal trig functions? Instead of SOHCAHTOA, we had CHO-SHA-COW. I don't know if anyone else out there calls it like that, but I like it. Okay, so tell me, what is the C here? This is sine. What is its reciprocal? Cosecant. Good job. Cosine, its reciprocal is secant, and the tangent, the reciprocal is cotangent. So right here we have 6 statements, and these are true statements, right? The cosecant of theta is 1 over sine of theta. That's a true statement, right? Sine is 1 over cosecant, secant is 1 over cosine, cosine is 1 over secant, tangent is 1 over cotangent, and cotangent is 1 over tangent. Okay, cool. 2 other ones that we're going to get here, and we've kind of talked about this before. When we're doing SOHCAHTOA, tangent is opposite over adjacent, right? When we put that on the unit circle, which letter is opposite and which letter is adjacent? Y is the opposite, good, and then adjacent is x. And then we were able to look at trig there and figure out what trig ratio was y. Sine, and x is cosine. So what we found here is that tangent is sine over cosine. And I think we've talked about that before when we were finding tangent of angles on the unit circle, right? Cool. What does that mean cotangent is going to be? X over y, which would then become cosine over sine. Awesome. So these are your basic identities that you're going to use to help simplify and prove that an identity exists a little bit later. Okay? Now, are those ones that seem okay? You can remember those? Okay, cool. Now, what we're going to talk about is the domain of validity. Let's just take one of these basic ones. Sine is 1 over cosecant. Okay? What did you guys tell me when we were talking about identities before? What can we not have in the bottom? We cannot have 0 in the bottom. Okay? Now, when I look at just plain old sine right here, sine is in the numerator, so do we care about that? No. But we've got cosecant in the bottom. And to make things a little easier, let's actually change cosecant. What is cosecant? 1 over sine. So I'm going to change cosecant to be sine. So now we've got sine in the bottom, and what do we not want to have happen? We don't want sine of theta to become 0, right? Because sine is in the denominator, and what happens if you divide by 0? Blows up, bad things, sinks your battleship, okay? So now, here's a question, and I'm going to let you think on it for about 30 seconds. When is sine equal to 0? You might be able to give me one value, but I want to come up with a way of expressing all the times with sine is equal to 0. So what I want you to do is take a second, and I want you to graph sine and look for a pattern for when it's equal to 0. Okay? I'll give you about a minute here. Again, you're graphing sine, and you're looking for a pattern. When is sine equal to 0? All right, let's kind of start graphing together. Ofa, can you help me here? If I'm graphing sine, where does sine start at? Yeah, good job, because the height, sine is height, and the height is 0, 0. How long does it take sine to go through one cycle? So then at 2 pi, so let's call that 1 pi, here's 2 pi. It's done, it's back at 0, right? So where else are we going to see x-intercepts here? At pi, we're going to see one, right? Because it's, so what it's going to do here, if we just graph one cycle, if this is 2 pi, it's going to go up to 1 at pi halves, come back, go down to negative 1 at 3 pi halves, look like that. Do you guys agree with that? That was one cycle of pi, but it's going to keep going left and right. Where are all the x-intercepts going to exist? Every multiple of pi, right? So if I were to keep going, I want to see it at 3 pi, 4 pi, 5 pi, 6 pi, right? Or over here, negative pi, negative 2 pi, negative 3 pi, negative 4 pi, right? So we're seeing this at multiples of pi. So what we're going to say, remember our whole goal here is to find what's called the domain of validity. That's basically us saying, what can theta not be? Kind of like earlier where we said x can't be 0, x cannot be negative 2 or negative 1. Here we're going to say what theta cannot be. Well, what values of theta make sine become 0? You said multiples of pi, right? So I'm going to say this. Theta cannot equal n pi, where n is any integer. So what's an integer? It's a whole number that could be positive or negative. So if I'm doing n pi, does that cover every x-intercept out there? Yeah? Does that cover 7 pi? Yeah, because n can be any integer, right? So this is going to take every multiple of pi and basically say, hey, don't let theta be any multiple of pi, because any multiple of pi will be an x-intercept, which would make it become 0. And what do we not want to do? We don't want to divide by 0. Okay, so that was a long answer to an easy question. The question was, when is sine 0? And the answer is any multiple of pi. So basically, guys, as we're going through these trig identities, if it says what's a domain of validity, if we ever see sign is in the denominator, what do we need to restrict? Or in other words, say that theta cannot be. Any multiple of pi, it's n pi, okay? Will you have that written down somewhere? I'm going to put that over on our sideboard just as a way of remembering. So if we have sine of theta cannot equal 0, then we're going to say that theta cannot equal n pi. Okay, cool. Let's keep on rolling here. Now, let's go through and look at this one, okay? It says, give the domain of validity for each identity. Eventually, we're going to get to a point where we're going to verify these identities and show that they are true statements. For now, though, we're just going to look and say, what are the denominators? And then what would make those denominators become 0, okay? So what we're going to do is, using these trig identities from on this page here, we're going to get everything in terms of sine and cosine. So I'm going to put a little side note here. Get in terms of sine and cosine. Okay, so is cosine okay? Yeah, we want sine and cosine. How could I rewrite cotangent? So 1 over tangent, technically that's true, but we're wanting in terms of sine and cosine. Good job, so that's cosine over sine. Over here we have 1 over sine, that's okay because we want it in terms of sine and cosine. And then we're going to have just plain old sine. Okay, cool. So now the question is, what is in our denominators? I see sine right here and sine there. Do we have cosine? Nope, just sine. So we're going to say we don't want sine to be equal to 0, right? Because what happens when we divide by 0? Bad things. So then, what does that mean theta cannot equal? We just answered that on the last one. What was it? Any multiples of pi. We're going to write that as n pi, where n can be any integer. So all we're doing right here, guys, is finding the domain again. We're saying we want to make sure we don't divide by 0, so don't let theta be n pi. You okay with that? All right, now we're going to do this next one here. Sine times cotangent of theta. Hey, we kind of already did something similar to this. How did we write cotangent before? Okay, what's the only thing we see in the bottom? Sine. So what does that mean we're going to say our restriction is? Okay. So we don't want theta to be, if we don't want sine to be 0, what does that mean we can't let theta be? Well, 0 is actually one of the options we can't let it be, but there's a lot of other ones. So what do we put? What do we put on all the other ones? Sorry, I should have put a cannot equals right there. Let's add that in there. Kind of a big deal. Theta cannot, if we don't want sine to be 0, what does that mean we don't want theta to be? N pi, or once again, n is any integer. Well, why is sine getting all the love here? What if cosine's in the bottom? Then what do we need to restrict? Well, that's what we're going to look at next, okay? And then what if they're both in there? We'll talk about both of those, okay? So, let's add a blank page here. And I'm going to have you just on your side space. We're going to see ones where we're going to get cosine in the bottom, okay? So, what do we do if we see cosine in the bottom? So what I want you to do is let's do the same thing we did with sine. I'm going to give you about a minute here, and I want you to graph cosine and ask yourself, where is cosine 0? And again, you're going to look for a pattern. So I'm going to give you about a minute here. Alright, good. So we're going to go to tau here, because I called on you. I was just making sure you're ready. How do we graph cosine, and what'd you say?
We start at 1.
Okay, so cosine starts at 1. What is the period? How long does it take to go through a cycle here? What? How long is it? What is the length of a cycle? Same with sine. 1 rotation. 2 pi is what I'm searching for there. And she knew it. She was just put on the spot. So she's like, dang it, Solberg. Ask better questions. All right. Okay, so cosine starts at 1, takes 2 pi to get there. So then at pi, it's at -1. So what are the x-intercepts? Half a pi, pi half, and what else? And so that was 1/2 pi. What was the next one? 3 pi halves. So if I started writing these out, I saw one at pi halves, 3 pi halves. If I kept going, where would I see the next one? 5 pi halves, 7 pi halves. If we kept going, do you see a pattern here? What's the next one going to be? 9 pi halves, 11 pi halves. Okay, hopefully we're seeing the idea, and then we're going to see plus or minus of these, right? We're going to see those in the negatives and in the positives. So what's going on in the numerator? What do all the numerators have in common? They're all odd. Thank you. I was like hoping you're seeing it. They're all odd multiples of pi. So how are we going to write that out? Because the last one, it was easy, right? They were all just multiples of pi, so we'd say, well, just don't let theta be multiples of pi. We're saying here we want theta to be odd multiples of pi halves. So this one is a little bit tricky. This actually, when I was in college, we had to write the definition